right. Hey, what's up, you guys? It's been a while, I guess. And I hope that you've been taking a look at some things that I posted over spring break and stuff like that. I didn't get a whole lot of responses from you guys, but I know at least a couple of you are at least probably looking at those and taking advantage of some of the review opportunities that you might have. You know that the test is still on, right, you guys? And so yeah, and kinetics could be on the test. Okay. I can, we'll meet together and talk more about that, but I want to introduce you guys to this idea of kinetics and what it means and in this little short lecture here. And I want to go ahead and get going because my recorder allows me a 15-minute window. So here we go. Feel free to pause along the way, and I'll have office hours if you have questions or problems, and we'll have some review to go along with this. So what is kinetics about, you guys? Kinetics is basically this. It's the study of how fast a reaction happens, right? So some reactions are really fast. You know, you drop sodium in water, you don't have to wait very long for the reaction to start, right? It's a fast reaction, okay? Whereas, you know, if you drop a piece of iron in water, you know that over time that iron is going to rust, right? But you're not going to see it. You're not going to register it by staring at it. Okay. It takes a long time. That is a slow reaction. Okay. So same thing here, right? This single displacement reaction would be a slow reaction. It takes minutes, if not hours. Whereas this reaction here, this double displacement, is instantaneous. As soon as I combine solutions of these two ionic compounds, you're going to get a precipitate of calcium carbonate right away. Okay, so how do we measure that? Okay, well, there's three ways that we can measure it, right? And they're all right here. Okay, and they're all measured at looking at changing concentration over time. And remember, when we talk about change in concentration, you guys, that means that we are looking at basically this, right? Molarity. So that's a capital M there. It's hard to draw with a mouse, you know, per second. Okay. Or the way that you'll see it a lot is molarity per second to the -1. Okay. So that's how we're going to show, or the units that we're going to use to measure rate of reaction. All right. So let's take a look at this. All right, here's different ways that we can do this, right? We can look at the disappearance of a single reactant. And the reason that there's a negative sign there is because the reactants are going to decrease, or their concentration is going to change negatively, right? So that means that we've got to put a negative sign in front because rates are always positive, right? You can't say, hey, I'm going -3 meters per second. That's not how fast you're going, okay? Same thing here. We can't have -2 molarity per second, okay? So there's one. We can also look at appearance of a single product. In this case, that would be positive, right? Okay, so here's a little example, you guys, of a reaction just to kind of get us started in looking at this at this kinetics, right? So here's where we start. Here's our concentrations over here. Here's where we end, and this is how much time has elapsed, and here's our new concentrations. So let's answer some questions about this. All right. First one is this, is find the rate of change for AB. So remember how we do that, right? Because AB is a reactant, okay? We're going to look at the change in molarity there. It started at 15, it ended at 5, okay, and it took 60 seconds for that to happen. So we plug that all in, okay, and we get this, right? 0.167 molarity per second, okay? Now, we're going to do the same thing for A squared and B squared. If we look back at that last slide, we started at 0 molarity and we ended at 5. That took 60 seconds. So here is our rate of appearance of the products, right? So how does the rate change for AB compared to A2? Okay, well, the change in our concentration of AB, right, is double that of A2. And this totally makes sense because if you look at the reaction up here, right, isn't it 2 moles of AB to 1 mole of A2? That totally makes sense that the rate of disappearance here would be twice the rate of appearance here. Now, If we wanted to do this, is there another way for us to find the rate of change for A2? The answer is this, yes. Let's check the next slide. So here's how we do that, you guys. Here's how we find the change in rate, you guys, of one thing. We look at the change in rate of one reactant compared to another. And if we multiply that by the fraction of 1 over whatever the coefficient is for that product or reactant, we can find the rate for anything, basically knowing the rate for one thing. So just to give you an example, right, here's our rate for our last reaction, which was AB, right here. And remember, it had a coefficient of 2 compared to our rate for A2, which was 1, which had a coefficient of 1. If we do the math, this all works out nicely. So we can use the rate of one thing to find the rate of anything in the reaction. All right, let me move myself here. Just a quick graph here to share with you guys. Here's our reaction up here. If you notice, you guys, NO and NO2 are basically disappearing and appearing at similar rates, right? However, O2 is produced half as fast, and we can see that because of the coefficients that are related up here. Okay. Now we can look at what's called an instantaneous rate by looking at the negative slope of by looking at the slope of the tangent for the reactants. Okay, we can just do that, you guys. That requires some calculus skills, and so frankly we're not going to do that here. However, we need to kind of understand this. All right, moving along, you guys. We're going to look at what's called a rate law. All right, so rate law is the rate of the overall reaction. So here's a rate law right here. Here's our rate law, okay? If you look, it's the rate, and then we've got this thing right here. We've got K. K is the rate constant, and that is specific to the reaction and temperature. So there isn't one rate constant. There's a rate constant for every reaction at every single different temperature. It gets wacky, right? Then we've got our M and our N. These are exponents that get attached on, and they tell us what's called the reaction order. And I'll explain that in a second. Okay. But that's going to be our main focus from here on out for the rest of the presentation, is how do we find this rate law and how do we find the reaction order for each of the reactants. If you notice, all that we use in the rate law is the concentration of the reactants. We're not worried about the appearance of the product. All right, so reaction orders, M and N, okay? You can't predict it from a balanced equation. So I can't just look at a reaction and go, oh, here's what M and N is. We have to have experimental data. And then we have reaction orders, right? We have 0, first, and second. Sometimes you might hear or see 0th order. Oh, sorry about that, 0th order. That's just, I don't know, it's a weird thing. Okay, but that means this, M or N can be 0, 1, or 2. That's basically your 3 choices. So to give you an example of some experimental data, here's some experimental data. And we'll take a look at this again later in the slideshow. But this would be what experimental data would look like. It gives you some different concentrations in combination, and it figures out what the rate of appearance, what the rate is for that reaction. So here we go. If you have a 0 order reaction, that means doubling the concentration has no effect, right? No effect on the reaction rate, okay? So that means right here, you guys, 0 order reaction means our exponent becomes 0. And that means this, right? If we were to graph it, doesn't matter what our concentration is, we'll always get a straight line, okay, with the same slope. All right, next one, first order reactions, okay? Yeah, I can hear all you Star Wars fans out there snickering. Okay, good. All right, so first order reaction means this. If we double the concentration, we double the rate of the reaction. So our exponent becomes 1. Second order reactions, okay, this is for the next Star Wars movie, by the way. All right. Second order reactions means if we double the concentration, we quadruple the reaction rate, right? And our exponent becomes 2. So that means M or N can be 2, right? Okay, so let's look at our experimental data that we had. What's the rate law? Well, let's check this out, you guys. First one is this. We're going to look at, okay, what's the change in C? Well, when I double C, right here, and I double C, my reaction rate doubles. That means it's a first order. So my change in C is a first order. Okay, then let's do this, right? Let's look at, okay, what happens if I change B? Well, if I change B, right, then my reaction doubles as well. Okay, so when B doubles, the rate doubles. It's also first order. So therefore, my rate law is just like this, right, you guys? B to the first, concentration of C to the first. There's my rate law. That's important to be able to do that. Okay, so now we've got this. We've got our overall orders of reaction for our single concentrations, right? And then we've got this. We've got our overall order of reaction. So our overall order of reaction, you guys, overall is this, M plus N. So we can have anything from 0 for our overall reaction all the way up to 4. Okay, so we call those 0, first, second, third, and fourth order reactions. Whew, that's a lot, huh? Kind of weird stuff. But what this helps us do is it helps us understand what's happening in a reaction. So let's take a look at a little bit more of a little bit of nuts and bolts and then a real kind of experimental data and stuff. So K, not only is K different for every reaction and at every temperature, it also has different units because we always need to have the rate be meters or molarity per second, right? So that means if it's a 0 order reaction, K has these units so that we can cancel, so that we can get to molarity per second and so on, so that we can cancel out units and get to the correct rate. All right, last one here. So here's more of a real reaction, you guys, with some experimental data. And the first thing we need to do is this. We need to figure out our rate law. So we do that. And I know this as I look at my reaction, I see, okay, right here, when I double NO, my rate quadruples. So when I go from 0.1 to 0.2 NO, my rate quadruples. So therefore, I have a second order for the concentration of NO. And then if I look at this, this is kind of weird, kind of hard to understand. But if I go like this, if I increase this one by 50%, my rate of reaction increases by 50%. That's like a 1-to-1 ratio. So I'm thinking that's a first order reaction. Okay. So yeah. So that gives me my rate, right? K equals that. The rate constant. Then I just plug stuff in. I use values from this table up here. Doesn't matter which values. You can choose any line. Plug them all in. That gives me my K. Okay. And then the overall order of the reaction, this is a third order reaction because if I add up my M and my N, I get 3. Woo! That's a lot. I know I covered this last part fast, but that's the nature of the beast. So after this, you guys, I've got some practice problems for you to look at that are attached in this lesson as well. And I will be available during my office hours. Those are posted on the Google Classroom. We can also put together a Zoom chat for our whole class in order to go over this stuff a little bit and take a look at practice problems. All right, you guys. Well, thanks for tuning in and have a great day. I will see you sometime this week.